Hi, thank you for that. So I am Alex Bradbury, and I'm one of the co-founders of the lowRISC project, which, as was mentioned briefly in the last talk, is a project which is a not-for-profit aiming to produce a complete open-source RISC-V system on chip. Now, I'm actually pleased to see there's a number of new faces here today, but being aware of the fact that many of you have seen me introduce lowRISC before, I'll try and just kind of condense the basic story of where we're heading to a brief introduction. Now, our fundamental aim is to try to bring some of the benefits that we see in the open source software world to the world of hardware, namely the benefits of many people benefiting from a kind of shared investment in a common code base. And we hope to do this by producing a complete open source reference SoC design for others to build upon. So whereas Krista was saying the RISC-V Foundation is primarily focused around this specification of the base RISC-V ISA and some particular extensions, and then as a separate project to that you have the Berkeley open source cores, our focus is very much on the implementation and in encouraging people to contribute and build on a shared implementation. Whereas, just as in the software world, if you were to start a large software project, you'd be almost crazy to do so without building upon some sort of open source base, whether that be the Linux kernel itself or indeed various other open source projects which have provide for hundreds of millions, billions of lines of code that we all rely on day by day. And I say here the aim is to be kind of the Linux of the hardware world. I suppose if you were to make a closer analogy, it would be a Linux distribution in the sense that we are working with other people who are developing code and specifications, and such as we hope that the main applications core would be the Berkeley Rocket implementation. So our aim is very much to write new stuff where necessary, but also to work with other people who are producing things and integrate it into a common, well-defined base. And one thing we hope to do that perhaps others who have tried to do something similar haven't been able to do is to produce volume silicon and low-cost development boards that are kind of Raspberry Pi for grown-ups. And this is, I suppose, the success of Raspberry Pi is partially an inspiration for this, as a number of us have been involved with Raspberry Pi since the beginning. And we kind of see that there's demand for something which is perhaps like it, but fully open in the hobbyist and developer community. So the project itself is completely not-for-profit, and we think that it's actually a standard base SoC platform. It makes a lot of sense that it comes from outside the usual players, i.e. it doesn't come from one of the existing incumbents, as you could certainly see problems there with concern about whether they're over-representing their own interests. And we're currently based at the University of Cambridge Computer Lab. So as for our funding, we are very lucky that a ex-Computer Lab member was keen to see open source hardware happen, has given us initial funding to get off the ground and indeed get through to our initial test chip and so on. We're also looking at more traditional research funding for the more research-oriented aspects of the project, and we're also recently been very grateful to receive a donation from Google, which is helping to expand our team. So the SoC itself, this gives a kind of rough diagram that I will have shown you before if you were here at the last workshop, showing what a test chip might look like. And so the two parts that I might make special reference to are the support for tagged memory, so the tag cache here, and here, which are what we call the Minion cores. So this is a collection of small, say, microcontroller class RISC-V cores located close to I/O, which can be used to implement soft peripherals, but also a variety of other uses. So you don't have to rely on a fixed hardware implementation of I2C, SPI, etc. You can to have a custom implementation which is modified at runtime, running in hardware, running in software. Now, I won't say much about tag memory because my colleague Wei, who's also here, is giving a talk tomorrow where he'll give a more detailed rundown of the status of the implementation and give a rundown of results in terms of performance overhead. I'll just say briefly that the major idea of tagged memory, which is not something new, it's been around since the early days of computer architecture, is that for each memory location you associate some additional metadata with it, which we call tags. And you might use this metadata to enforce some access control at a fine granularity. So for instance, mark a particular word as being read-only or write-only. And so this has one particular application, which we describe in more detail in a memo we published towards the end of last year, which is in terms of producing control flow hijacking by marking code pointers and vtable addresses as being read-only. But also other uses such as for garbage collection, infinite memory watch points, or indeed full empty bits for synchronization. The other thing I'll just highlight is that so Wei's the one who's done most of the work in terms of building on top of Rocket and integrating tagged memory support into the code base. And as well as doing all that implementation work, he's also done a really good job of doing a detailed tutorial about downloading the tagged memory implementation we have available, and as well as describing how that work was done, he's also gone through and detailed how we made those changes. So for anybody else who's trying to work on the Rocket code base, hopefully you'll find that a useful resource, and we can start to grow the amount of documentation around the Rocket core. Now, Minion cores, as I mentioned, these are the original motivation was for soft peripherals, so solving this problem where often you end up with, even with a very powerful system on chip, but actually you end up having to connect to an external microcontroller because you want some interfaces that aren't supported, or you want some real-time control. And so this requirement for real-time obviously points you towards a simple core implementation, kind of 3 or 4 stage pipeline, support for scratch pads rather than simply instruction caches and data caches. But there are also a number of other uses that we're interested in exploring. And I think perhaps one of the more interesting use cases when you combine the Minion cores with tagged memory. So for instance, have a Minion core subscribe to events such as accesses to words which have a certain tag, and then the user's software can then implement more fine-grained security policies in response to that event. Another kind of obvious use is, of course, for secure isolated execution, where you can have software running which cannot be, with support for carving up the memory space, cannot be touched by application code running on the kind of main core, and can run with a much smaller trusted computing base. And I suppose a kind of long-term vision for this is to work to have minions distributed throughout the SoC. So in the was a look to perhaps in the extreme case as a research question, how much of the fixed function hardware that you find throughout the SoC could you replace with potentially quite customized or quite stripped down RISC-V cores in order to increase the amount of customizability or reprogrammability. And so the roadmap for I said the core roadmap here because there's actually quite a lot of work going on in the kind of wider low-RISC and RISC-V community that we hope to build in, which I'll talk about shortly. But our main plan for our development based around Cambridge is, well, firstly, our focus is on what we call untethering the SoC. So whereas now the Rocket relies upon communicating with either an ARM core on the FPGA on the Zinc or an external system via the host target interface for basic I/O, Wei again is currently working on removing that requirement, so having standard peripherals so that you can boot Linux in a standalone environment on a FPGA, and indeed hopefully on a low-cost FPGA, just like the D Nano is enough to boot an open RISC core. We'd hope to have a similar demo up and running for RISC-V. And again, later in the year, we also hope to distribute an FPGA-ready implementation of our Minion cores, which people can start to play with and start to look at implementing peripherals and so on. And towards the end of the first quarter of next year, we'd hope to tape out a dual or quad-core test chip with integrated memory controller and PHY, Minions, and so on. Now on to work which has been going on over the last few months. We are very fortunate to be part of Google's Summer of Code program, which is just reaching the halfway point around about now. For those who aren't familiar with it, essentially Google provides sponsorship for a number of open source projects to work with a number of students who kind of work as almost remote interns. So we have a number of community members who are mentoring these projects, and we actually found a little bit of extra funding to add a few more projects to this as we found there were so many applications which we're really interested in doing. So I can certainly talk to you in more detail about any of these if you want to chat to me later. One I might draw particular attention to is porting the port of SEL4 to RISC-V. So SEL4 is an L4-based microkernel implementation with a formally verified core, which was open sourced, I think, sometime last year. So the student who's been working on this, Hesham, has been making very rapid progress, and he's been rushing away. He's got a basic port of muzzle libc going. He's mainly having issues now with the lack of support for the 32-bit SV32 in Rocket Core, whereas SEL4 is unfortunately somewhat 32-bit limited. But if you're interested in security on the RISC-V platform, which I know from my previous discussions many of you are, that might be something you want to look at. We've also had two students who've just finished their master's dissertations, one on uses of tagged memory, another looking at what we call the shim might look like for the Minion cores. So I mentioned that Minion cores provide a way of implementing soft peripherals, but of course, relying on a pure bit banging approach is very, you leave a lot of performance on the floor. So a question that this student looked at was what it might make sense to put into hardware to offload some of the basic tasks, such as shifting out a register or doing a parallel load into a register. We have new PhD students, new staff starting October. Well, today, in fact, we've got another two local interns at the lab working on low-risk and tagged memory-related projects. And over the past few months, we've been really pleased to have a whole series of discussions and kicking off collaborations with startups, more established companies, and other academic groups, which has actually come about at a much earlier stage in the project than we'd anticipated. Indeed, if anybody wants to we're very keen to collaborate with anybody else who has an area of interest, so please do chat to me later. One common area of interest we've been finding is in terms of security features. So I mentioned tagged memory as a way of providing useful, adding additional security features, but there's also more standard security features that you'd find on any common SoC on the market, or at least available on the market, such as support for secure boot, crypto accelerators, encrypted off-chip memory, isolated execution, and so on. And so we're starting to build up a small number of people who are interested in producing something like an open SoC security specification. So what would we define as the base requirements to support these techniques? What's required in the different parts of the SoC? And can we offer it with a sufficiently low overhead that nobody would want to turn it off? Because, of course, one of the problems with some of the existing solutions in the market is that you look at one SoC and it supports part of the spec, but not another's part. And again, we want to have a fully open specification so that you can verify and audit the implementation, and there's no reliance on NDAs as some kind of security by obscurity protection. Another piece of work which has been going on, and this is thanks to Stefan Milentowitz, who unfortunately wasn't able to make it over to this workshop, or else hopefully be giving a talk himself about his ideas for debug. So he's given me a few slides of what he'd like to introduce to you. So some of you might know Stefan from the OpenRISC community. So he's done a lot of work on OptimSoc, which is a many-core OpenRISC implementation. And as part of that, he did a lot of work on trace debug, because of course, you have a many-core system, and debugging when something goes wrong is tremendously difficult, and it's very useful to rely on a trace of events to look after the fact to see what happened in this many-core system. And this is something that we're actually developing kind of out in the open. So if you go to fab.lowRISC.org, which is our kind of project management site, we have a whole bunch of extra information there on the wiki, and we're very interested in talking to people over the course of this workshop. Now, the two basic debug modes that we hope to support are your traditional run control debug, so what you'd get from GDB with breakpoints where you have a particular program counter, you want to stop it there. And this is actually the aspect where we have less work, and we'd be very interested if other people have experience or thoughts or know of an existing open implementation we might base on. And then, of course, there's trace debugging, which, as I mentioned, gives you, well, with a many-core system, you no longer really have a single program counter, and so actually deciding how a breakpoint would work or what a breakpoint would mean can be very difficult. And so a lot of people find that actually having a trace of events and then analyzing what happened after the fact to be more useful. And so we're working with Stefan to migrate some of what he worked on OptimSoc and integrate it in a way that makes sense in the RISC-V ecosystem for the rockets and the low-risk implementation, and something that hopefully other people can hook into and build upon. Now, I can't really, this is more of a, I suppose this slide is more of an advertisement to either go and look on the wiki or indeed visualize afterwards, or come and chat to me later, so I can't discuss in full detail. But I'll point out that one of our hopes is that is that you can build the run control debug and trace debug on the same basic infrastructure. So we're building upon so this GLIP project is part of the work that, see that? Yes, that Stefan and some of his collaborators worked on, which is basically providing a simple FIFO-like layer, so a way of streaming trace events off the SoC. We'd also be interested in looking at some of the features that you're seeing in more modern SoCs, such as the ability to write trace events directly to a page in memory. And so, yeah, I'll just leave it there just to say that if you're interested in getting involved, look at our website, our mailing lists, particularly our Fabricator instance, if you want to look at debug or any of the other directions we're currently looking to go in. We hope to start putting out kind of more detailed documents that describe, that kind of match our implementation as we go along. I'll also say that we've been having a chat with some of the people who organise the Open RISC conference, and so we're hoping that we can have a European low-risk/RISC-V event in October at some point. So if you want to express your interest in that, that'd be useful for us to know that people would enjoy that. So hopefully that would be co-located with the Open RISC conference, which is going to be in CERN in October. So we'll either merge it completely or else we'll add on an extra day or two afterwards. And so I'll open the floor to any questions. Thank you.
I'm curious what version of RISC-V you're using for your minions. Are you using the RB32E or the compressed instructions or anything?
So that's one thing that's kind of partially in development. So we've been talking to the ETH Zurich guys. So we've got a talk from Sven tomorrow about their work adapting pulp to RISC-V. So it's very possible that we will end up building on top of the pulp implementation, though we're also interested in seeing where the Z-scale implementation has come to. I think we need to run the numbers in terms of determining exactly what version of RISC-V to run, in that RV32E is obviously tempting for area reasons, but then it depends on the use cases, because if people want to use it for a slightly more general offload, then having a slightly beefier core makes a little bit more sense. And it would be that much nicer if you had 64-bit registers, so you had an easy ABI compatibility between code running on the application cores and on these Minion cores. So I think that's partially work that remains to be done in terms of running the area numbers and looking at potential use cases.
Peter Shu, Oracle Labs. What kind of memory controller are you using, and what is the status of it?
So we're talking with a, oh dear. We're talking with a number of providers about memory controller and memory PHY. So we haven't currently decided on the memory controller and PHY that we'd use on final tape-out, with the two, of course, being quite linked, where obviously many providers provide the PHY and controller as a pair, where technically you could separate them, but in practice you probably don't want to. We haven't, I can't publicly confirm a controller that we've decided upon, but we're talking with a couple of vendors, and it'll come down to availability at a reasonable cost, and also availability of people to help us integrate it as we've done. So this summer we're working on a 40 nanometer test chip for 128 core research design called Loki. So this kind of predates our RISC-V work using a custom instruction set, and we found that it's worked quite well for us to produce the RTL ourselves, so the core Verilog, but leave final sign-off to a third party. So there we're working with IMEC, for instance, to do a final physical layout and integration, and we expect to do something similar for low risk. And so it'll come down partially down to which house we choose for that, and then which PHYs they have expertise with.
If you're porting SEL4 to this,
Yep.
I assume you're using the supervisor instructions.
Yes.
And are you developing formal semantics for those instructions and re-establishing the SEL4 proofs on top of those?
No, not currently. The SEL, I think that the subset of SEL4, which is formally verified, is perhaps less expansive than one might like. I forget the exact details, but I think that it's only one of the ports which is verified currently.
Yeah, only ARM right now.
Sorry, it's the ARM one, is it? Yeah. So that we're very interested in having a full formal spec of RISC-V, and I know Krista and the rest of the team at Berkeley are interested in that as well, particularly things like memory semantics. But that's not part of the current porting work which is going on. But yeah, that would be a really useful kind of next step.
Thank you.
Any thoughts on how the code for the Minion cores, where does that live? Is that something that goes in the Linux tree and we get a subsystem to distribute code out to co-processors? Have you got any thoughts around that?
Oh, as in how you program them for devices?
Yeah,
Or?
yeah. And security around that as well.
Yeah, so there are a couple of choices there. So, I mean, one idea from, again, talking to some of the Berkeley guys last time was that if you wanted to implement a soft peripheral, perhaps you might do that in Chisel, and you'd have a back end that would generate assembly, RISC-V assembly, and with some support for our shims for your I2 CSPI. There's kind of the higher level question of how would you then integrate that with, say, the Linux kernel. Would you have something like so one way is something like Graybus, which Google have been using for Project Aura, which Greg KH implemented, which is just a kind of a layer on top of UniPro that gives you a very simple pipe where you have a kind of traditional hardware interface at the other end. But that perhaps leaves something on the table in terms of the performance and the possibility that you have when you have a full programmable core, because you're kind of emulating a traditional hardware interface probably isn't the best way of using your resources. You'd probably want to have a higher level interface which will only wake up the application core exactly when needed. There's a number of options in terms of and it would be nice to be able to reuse as much Linux kernel code as possible, but yeah, exactly how to get somewhere between either completely ignoring the possibilities of Minion cores or writing a completely new set of drivers there's not a clear way forward currently. So again, that's something we'd be interested in exploring with anybody who has, particularly anybody with lots of Linux kernel hacking experience.
You said you're going to have volume production in 2016. So how does that going to work with an open source project? Are you going to anticipatory build a lot of chips and hope you can sell them, or you'll get pre-orders before you make any? What are your thoughts?
Yes, so we'd hope to get a reasonable number of pre-orders, and we also hope to provide enough features that some of the companies who we're working with who are interested in use for test devices or perhaps smallish volume, so in the tens of thousands, would be able to make commitments. So yes, pre-orders certainly help a lot, and
So are you thinking like 100,000, 10?
Yes, you'd have, yeah, with a minimum run of wafers, we'd end up with 100 to 200,000 chips. Yeah.
I haven't seen any graphics in your block diagram. Are you planning to modify or extend the RISC-V to do graphics?
I mean, in the initial version, no, other than possibly simple frame buffer support. We don't have a current plan for a RISC-V GPU. We'd hope to work with others on developing that in the future, but we kind of feel so with, we haven't been short on ambition for the initial test chip, so I think adding GPU as well might be perhaps a little bit step too far. We can push that one back till V2. But I agree, a GPU would be of great interest.
A question, have you thought about crowdfunding sites to raise money?
Yeah, so I guess that comes back to David's question. So certainly once we have a working test chip back and we have a full plan for volume production, that would be a very good time to go to one of crowdfunding sites for people who want to pre-order the Raspberry Pi style development board. We feel kind of, morally we want to have a very, very clear plan of exactly what we'll produce, when we'll do it, and a very clear path to doing that, as we don't want to expose end users to very much risk.
Yeah, I'll just pass it on, but I just want to mention we should probably say name and affiliation when making the question so people get to know each other.
Hi, this is Sam Falvo, no particular affiliation. In fact, I'm the only one here like that. So with such an aggressive delivery schedule, one of the things that I've not seen mentioned so far is documentation, by which I mean data sheets, app notes, things like that. How do you plan on, what's the development process for documentation?
I mean, we hope that will improve as we get more resource on the project. We're able to spend a bit more time on documenting it, because I think that, we do recognize that documentation and kind of educational materials of some sort are key to a project, both in the kind of medium term and the long term, because the only way we can get new contributors is if people are able to make modifications to the core. And if our goal is that people can use it as a basis for new SoC, we're not going to meet that goal if it's completely undocumented. So I agree, documentation is something that we need to work on, and our hope is that for each of these projects we'll have a amount of time that will be dedicated, kind of sub-projects, an amount of time be dedicated to producing documentation.
Don Stark from Google. What other interfaces were you thinking of having on your test device beyond just the memory controller? For example, will it support PCIe, or what other relatively high bandwidth interfaces might be available?
Yeah, so I guess there's the initial test chip versus a later. So we might end up doing several test chips. It depends. Obviously, for the first test chip, we'd like to integrate as much IP as we have access to and can reasonably integrate. So PCI Express would be very nice. It would also be, we're also talking to a few vendors who have SerDes IP, kind of something like you have on modern FPGAs, where you can use it for PCI Express or SATA or USB 3, which would be kind of ideal, particularly as more of a research question or a longer term goal. It'd be nice if you could use something like the Minion cores, not just for low speed interfaces, but for providing controllers and Macs for Ethernet, SATA, USB, so for more high-speed protocols. But yeah, PCI Express would be an obvious target.
Okay, thanks again.